All right, today we are starting our volume unit. This first page is just a collection of the formulas we'll be using. So we'll really do these kind of as they come and review what they are, but this is your one place to check for one that you need. But for example, today we'll work on prisms and cylinders. Pyramids and cones will be worksheet 3, I believe, and spheres are in worksheet 2. So we'll take them one step at a time. So this first one, we are really focusing on prisms for the most part. Part 1 says match the following terms to the diagram. Given the rectangular prism with face BCFE, so BCFE is this bottom side here, use each value only once. So I like to go with the letters first and then match them. So rectangle ADHG is this top side, so we would also call that a base because it's straight across from our other base. I'm going to put that right here. HF is a side, so we could call that an edge, or actually we would want to call it a height. It's our vertical side here. AD we'll call an edge. Lateral face means one of your vertical straight up and down faces. So that'd have to be this rectangle HDCF, which is the blue one here. And then vertex is any corner point. So point B would be one of our vertices. Number 2, properly name the following prism. So really you're naming it with whatever shape its base is. So here this is a cube. Okay, a square prism, if the square is your base and your height is the same as well, then it is a cube. Number 2, our base is a triangle. So we'll call this a triangular prism. Here we have a parallelogram as our base, so we'll call it a parallelogram prism. And then this one has a hexagon base, so we'll call it a hexagonal prism. So you just name them with whatever their base shape is for the most part. Cavalieri's principle says here, if two solids have the same height and same cross-sectional area at every level, then they'll have the same volume. So we're going to talk about what that means. So here my cross-section, or just one slice, if you will, is 3 by 4 all the way up, and then I'm going to have a stack of 15. Here my cross-section is also a 3 by 4. So even though it's slightly tilted, kind of like a leaning tower, it's still going to have the same cross-sectional area since the dimensions are the same, and then it has the same height. They're both up here at 15 centimeters. So they will have equal volume. So I'm going to go ahead and type instead of right here. Let's make this smaller. Same cross-sectional area and same height is why they would have the same volume. Okay, we're using Cavalieri's principle there. Number 4, Jenny says the two prisms do not have the same volume because their cross-sections are not the same. Renee disagrees. She says that it isn't this shape that has to be the same area. Renee thinks they have the same volume. Who is right and why? Okay, so they don't have to be the same shape as long as they have the same area. So here we had a more perfect square. This would be more of a parallelogram, so they're not identical shapes. So here they don't have to be either. So if we talk about our green area right here, I would have 1/2 times 5 times 12, which should give us 30. And here I have, for my yellow square there, or rectangle, 5 times 6 also gives me 30. So since they have the same area of their cross section, and then they're both 10 as their height here, then they would have the same. So in this case, Renee is right. Both prisms have the same cross-sectional area. And height. Okay, last one for this page. When a glass box is tilted on its side, the water inside shifts places, but no water is leaking out or anything like that, so our water should maintain its original volume. What is the relationship of the volume of water before and after tilting? So I just mentioned that part. The volume remains the same. We didn't have any leaks, we didn't add any water. And then what is the height of the water when the box is tilted upright? So what we're going to do is we're going to find the volume of the water by doing 27 by 12 by 5. We don't want to use 18 because the water doesn't go all the way to the top. So we'll use 5 instead here. So we have volume equals 27 times 12 times 5, which is 1,620 cubic inches. All volume will be units cubed. And then here, if I know my volume is 1,620, then I can do 12 by 18 by our missing value for this piece of our rectangular prism. So 12 times 18 gives us 216. So we'll take 1620 divided by 216, and we get 7.5. So 7.5 inches should be that height of the water on this prism. Next page. Jared wants to test out a new theory. Instead of having the cross-section areas the same as Cavallari suggested, he wants to have the radius of one cross-section and then double the height to make up for it. He believes because he divided the radius by 2 but doubled the height that the volume should be equal. Is he correct? So let's go ahead and label these. This is 1 and this is 2. And we'll just find the volumes and then we'll compare. So for this one, my radius would be 4. And for a cylinder, we have pi r squared times height. So I'll have pi 4 squared times 5. And this is where we're using area of the base times height for any prism. So for us, area of the base is pi r squared, and then we're doing the height of the prism. So let's go ahead and leave these in exact form. This would give us 80 pi. And then we'll take a look at the taller prism. So we have a radius of 2 centimeters this time and a height of 10. Which should give us 40 pi. So he was wrong. It is not the same. He was incorrect because when we square our radius, it is not the same as doubling. So because we are taking 4 squared to get to 16 and 2 squared only gets us to 4, we need to more than double essentially. Describe the solid that is formed by rotating each of these figures about the line M and sketch it. So if I took this triangle and I rotated it around the line they give us, I would end up with a cone. So try to curve this here a little bit. We would end up with a cone. If I take this rectangle and I rotate it around, I'm going to end up with a cylinder. If I take this circle and I rotate it around, I'm going to end up with a sphere. What's interesting about this one is these three were touching, so they're not going to have any gaps. They're going to be solid. When you have a gap like this, it's actually going to make it hollow. So let me see if I can draw this here. It would look something like this, where we're going to have a hole in the center. So we'll call this a donut shape. Here, we're also going to have that hole in the center. So it look kind of like this. So you can say a hollow cylinder or something, think of like a toilet paper roll. For this one, we're going to have a hollow sphere. This one is going to be a cone stacked on top of a cylinder. So I'll say cone plus cylinder, and it'll have a composite volume, meaning we could find the volume of the cylinder and then the volume of the cone and add them together. And then this would make kind of a hollow cone. Think of like an ice cream cone. All right, determine the volume of the prism / irregular prisms. And so for a regular prism, we want area of the base, so we use capital B, or sometimes you'll see AB for area of the base, but I like to use a capital B and then H for height. So area of my base here of this triangle is 1/2 base times height, and then height of the prism, which would be 8. So it looks like it would be 144 cubic centimeters. Here, what I would do is I would find the volume of the whole cube, and then I would find the volume of the small cube and subtract. So let's start with the whole cube. I'd have 12 times 18 times 10. Which is 2,160 And then for our little cube here, it looks like we have 5 by 10 by, if this is 5 and 5, then that would leave this as 8 if I subtract 10 from 18. So 5 times 8 times 10 is 400. So if I do 2,160 minus 400, I end up with 1760 cubic centimeters. Okay, our parallelogram here, we would have base times height for the area of our base, or this one face here, so 6 times 8. And then times the height of our prism is 7. So 336 cubic centimeters. All right, some more examples here. A king-size waterbed has the following dimensions, and it takes 240.7 gallons of water to fill it, which would weigh 2,071 pounds. What is the weight of a cubic foot of water? So here where it says feet, we have to keep that in mind because currently we are measuring in inches. So first, let's go ahead and do just the volume in inches. So volume would be 72 times 84 times 9.5, which is 57,456 cubic inches. Now, if I want to convert this to cubic feet, we have to remember that since our units are cubed, we're going to have to also divide by 12 cubed instead of just 12. So we would end up with 33.25 cubic feet. And then that weighs 2,071 pounds for 33.25 cubic feet. And we're rounding here, so we'll say it's approximately 62.29 pound per cubic foot. In part D and E, solve for the missing side length given the volume. So last two for today, we're going to plug in what we know. So for this prism, we want volume equals 1/2 base times height for the triangle times the height of the prism. So these are different heights, just FYI. So here I have an equilateral triangle, which is going to make this a 30, 60, 90. So if my hypotenuse is 4, then my short leg is 2, and my height here is 2√3. So for my base and height of my triangle, I'll use 4 for that full side, and then 2√3 for my height. And then we don't know this height, so I'll leave that as h. I'm going to replace this volume with 32√3. And now we can solve for h. Right away, I'm going to go ahead and cancel my √3 since they're on both sides. And then 1/2 of 4 times 2 is going to give us 4, h, and 32. So we'll divide by 4 to get 8 for our final answer for that dimension. So 8 centimeters is what we wanted. On letter F here, what I would do, since this height is not the same, consistent all the way, we're going to say that 11 is the height of our prism and that our base area that we need is of this trapezoid. So for our trapezoid, what we do, so area of a trapezoid is 1/2 B1 plus B2 times height, and then we'd have the height of the prism. So now we'll plug in what we know. We know that volume is 605. We're trying to find B1. This is also B1. B2 is 8, and then height is 5, and then height of our prism is 11. So now we'll go ahead and simplify what we can. I'm going to distribute here. Well, actually, before I distribute, I need to multiply 1/2 5 and 11, which is 27.5. And then we'll distribute. So 27.5 B1 plus 220, and now we can solve. 385 equals 27.5 B1. So I end up with 14 is that B1 dimension, that base one. And we were doing centimeters there. All right, now you can move on to working on worksheet 1 today.